Good day to all the lecturers and my fellow friends. I am Tanya Han, and today I'll be presenting on the poster titled Selective Oxidation of Methane to Methanol using Gold Clusters, the study of oxygen activation on gold clusters. The current process of direct methane to methanol oxidation comes with some limitations, which include strong carbon-to-hydrogen bond of methane and suitable oxidant for the direct oxidation process. Herein, this work proposes the use of gold catalyst along with oxygen as oxidant to overcome the limitations. Additionally, computational analysis is conducted to study the activation of oxygen molecule onto gold clusters through optimization and energy calculations. Now let's move on to the introduction. The process of methane oxidation is a one-step process of converting methane to methanol, which is preferable over the indirect syngas route due to the operating conditions which are less intensive and able to bypass the synthesis gas step, which result in higher energy efficiencies. However, the direct methane oxidation comes with its own challenges as well, which include strong carbon-to-hydrogen bonds of methane, which makes it hard to activate. The product of methanol is also highly prone to oxidation compared to methane. Although many oxidants were explored, they still suffer from some limitation in terms of suitability. These are the objectives, which includes analyzing the performance of gold cluster catalysts in the direct oxidation process, determine the suitable type of oxidant for the process, and finally, optimize and calculate the binding energies of absorbed oxygen molecule onto gold clusters through density functional theory calculations. These are the required steps when conducting computational analysis through density functional theory. First, we need to determine the suitable computational methods. The next step is to create the structure, which in this case includes oxygen molecule and a series of gold clusters including gold 13, 18, and 22, whereby the numbers represent the amount of gold atoms present in the structure. Next, the optimization stage, which takes into account the multiplicity of spin factor, whereby different quantum states will differ in terms of energy levels. Finally, energy calculation involves determining the binding energy. Now let's move on to the results and discussion. It could be divided into two sections, namely the geometry optimization and the binding energy. So for the first section, these figures represent the top and front view of the fully optimized structure, including gold 13, 18, and 22, as well as the oxygen molecule. For the next section, these three figures represent the optimized structure of oxygen molecule absorbed onto gold 13, 18, and 22 respectively. Now when it comes to the absorption process, gold 18 is the most stable with the lowest amount of energy and strongly absorbs onto oxygen. This result is consistent with other studies indicating that oxygen is more strongly absorbed onto smaller and evenly sized gold clusters. Additionally, binding energy that are relatively low were shown to be conducive during charge transfer from the gold cluster to oxygen molecule. So in conclusion, the objective of this project was achieved whereby all gold clusters were successfully optimized and gold 18 was found to be the most stable with the lowest amount of binding energy which strongly absorbed to oxygen molecule. These are my reference. That's all from me. Thank you.